Dr. Itajim Majumdar to the session. So over to you, sir.
Thanks a lot for the introduction and thanks a lot for having me here. Yes, yeah, I mean, I am always very happy to be back in this FDP, and every time I say this, that this seems so wonderful that weekdays, this kind of time, and so many attendees are joining, and they are always so like active, asking questions and uh, hearing the session very carefully. So it's really a pleasure of mine to be here. Let me first share my screen and then. Okay, great. So how do I? So let's get started with today's session, which will be on quantum error mitigation today and tomorrow, both. Um, there will be some overlap with some of the previous talks that I gave, but maybe not all of you were present in those. But yeah, I assure you, like, it won't be just a repetition of just what I did over the last few of these sessions. So we will start with very simply, we will start with mainly measurement error mitigation, talking about that, and then we will move up to, at least that's my plan, that we will move up to zero noise extrapolation and those kind of things. In particular, for measurement error mitigation, I want to just go through it a bit more detail, because it's very simple to understand. It's also very simple to implement. If time permits, what I would really like to do tomorrow is to show you some other techniques which are beyond what we think of as traditional error mitigations, which are at use currently, and those can actually bring a lot of improvements to the circuit executions that we have. So let's get started with this. And throughout today and tomorrow, whenever we talk of theoretical stuffs, we will always say that a qubit, whenever I talk of qubit, a qubit will always mean a density matrix. Yeah, I don't know how many of you were present in the last QT. We almost had an entire session on density matrices, so I won't go into those things here. But a density matrix in general is represented by rho, and it has mainly two properties. That first property is trace of rho should be equal to 1. What it means is basically that the trace of rho, that means the diagonal elements of rho, gives the probability of measurement. It's a density matrix, so the probability is no longer square or modulo square. That's when it is in state vector. If in state vector, if we have alpha 0 plus beta 1 as, say, my psi, then the probability of outcome 0 is mod alpha square, and probability of outcome 1 is mod beta square. On the other hand, if I create a density matrix out of this, this will be like this, psi. So this becomes alpha star 0 plus beta star 1. Remember, alpha and beta are in general complex numbers, and we have alpha 0 plus beta 1 here. So if we write down, we get mod alpha square 0 plus, say, alpha star beta um, 0 1. Okay, I apologize, this should be this and this should be the other way, but anyway, plus alpha beta star 1 0 plus mod beta star 1 1. And the moment we write down the matrix from here, we get mod alpha square here and mod beta square here. The other two terms will be the off diagonal terms. These terms are not part of measurement, when we measure, this is the probability corresponding to 0, and this is the probability corresponding to 1. Right? These two off-diagonal terms are often called coherence, and they kind of denote the quantumness of a system, but we are not going deeper into density matrix today. So since the diagonal elements are the probability of measurement, they should always add up to 1. So we get trace of rho equal to 1, and we should have rho should be greater than or equal to 0. What it means is it should be positive semi-definite. What it means is that all the eigenvalues should be greater than equal to 0. So when we write rho should be greater than equal to 0, what it implicitly means is that the eigenvalues of rho should be greater than equal to 0. Um, what again, this actually comes from the idea of probability, that the eigenvalues gives us the probabilities and the eigenvectors gives us the corresponding state where the system will collapse when we measure. So since these are probabilities, they should all be non-negative. This is what it says. Now, if we think of this rho, there can two things can happen. If we take rho square, so rho times rho, and if we take the trace of that, it can either be equal to 1, which means that rho is called a pure state, or it can be less than 1, which is called a mixed state. Example, if you take an example that let's say I have my psi is equal to 0, simple example, then my rho will be 0, 0. This is a pure state. So pure states, you can think of this that pure states are any state which you can also represent as a state vector. But there are certain states which you cannot represent as state vectors, and those are basically the mixed states. Now if you do rho square here, what will happen? This is rho times rho. This inner product is equal to 1. So we get 0, 0. That means rho square is equal to rho. And we have already seen that trace of rho should be equal to 1. So trace of rho square for this example should be equal to 1. It is called a pure state. That means it has a state vector notation as well. What is a mixed state? So if we think that, say I have a say I have an apparatus, which will prepare the quantum state for me. Ideally, I want to prepare my quantum states in 0. But the apparatus, since like no apparatus is exactly perfect, it almost always gives the outcome 0, but sometimes it gives the outcome 1. So with some probability p, it gives an outcome 1, and with some probability 1 minus p, it gives the outcome 0, where p is very small. Now, if we think of how do we represent this, how do we represent this kind of scenario mathematically? So if you think a general way of saying that, okay, why don't we represent this as, say, something like phi 1 root over 1 minus p 0 plus root over p 1. Maybe you can think that, okay, let's represent it like this. But this is completely wrong if you think. This is completely wrong. Why? There are many ways we can argue about why this is completely wrong, but the main thing you can understand is what this is a superposition state that I wrote, and a superposition state means it is both 0 and 1 at the same time. The scenario that I am creating here, it is not the same as a superposition. It is either creating 0 or creating 1. It is not creating a linear superposition of 0 and 1, but it is rather the combination, or you can, if you think the combination of states, it is a classical combination. It's a classical probability. There is nothing quantum about this. It's kind of saying that I have a biased coin and I toss the coin. Most of the time it turns out to be heads, sometimes it turns out to be tails. It's a biased coin. So that's an entirely classical scenario. There is nothing quantum about that scenario. Similarly, when I say that my apparatus is faulty like this, there is nothing quantum about this. It's a classical scenario. And this classical mixture we cannot represent using a state vector. There are many other things we cannot represent using a state vector notation. For example, if you have an entangled state, and if you try to find out what are the component, what are the representations of the component qubits, you cannot do that using state vector notation. But let's stick to this. I mean, this will be sufficient for us. So how do I represent this? I can represent this as, this is 1 minus p 00 plus p 11, and this is a mixed state. If it is not immediately obvious to you, I would request you to go back after this lecture and just write down the matrix like this. Take the square of the matrix, take the trace, and you will see that the trace will be less than 1. And you can understand why it will be, because the moment you take this 1 minus p square, that will be less than 1 minus p, and p square will be less than p, because both of them are decimal numbers. Both two, when you add those two, it will be less than 1 minus p plus p, which is 1. So this is a mixed state, and this mixed state notation is very, very important the moment for every type of noise that we want to deal with. And what we saw here is actually one of the first examples of noise that we can think of. So let's think of that I have a quantum circuit, say Q0, Q1, up to some Qn in qubits, and I have some quantum gates acting on the circuit, and say dot dot dot. And finally, you go and measure the qubits. So what are the different kind of errors that can happen here? There are multiple type of errors that can happen. First, state preparation. Can you, if you see that the requirement that we always say that all the qubits are prepared in 0. That's one of the DiVincenzo's requirement for quantum computers. So state prepared are in 0. But if you ask me, can you guarantee that? I will say no. State preparation, most of the time maybe it will be 0, but sometimes maybe it will end up being 1. Second, if you ask me what about the gates, the unitary operators, there are some rotations by say some angle theta. So if I ask you that just do this angle theta rotation, can you do that perfectly? No, you will end up doing some theta plus delta theta rotation. So exact um, rotation. So exact rotation is not possible, means exact implementation of the gates are not possible. So if you think of gates, the gates are also erroneous. If you ask that, okay, when my qubit is sitting idle, say my qubit is sitting idle in this part, can you guarantee that the qubit is in a correct state for this time when it is sitting idle? No. There, the qubits can actually, there is a tendency of the qubits in two ways. First, if you take the qubit in a higher excited state, this we have studied in say class 11 or 12, that an electron will, which in the excited state will try to give away that extra energy spontaneously, and it will come down to the ground state, to some lower orbital. So this is called decoherence. And similarly, if this system is in a superposition state and if you keep it idle, it starts acquiring some unwanted phase. So we'll take everything in decoherence. And the fourth thing, if you ask, is measurement, finally. So are measurements perfect? No. Even measurements are noisy. What it kind of shows is that everything that you do with a quantum computer, each and every basic steps are noisy. And of course, the things are getting better and better with every generation of hardware. But still, I mean, states are noisy. I mean, everything that we do are noisy, and we cannot do anything about that at this moment. Error correction is, of course, the path that we want to go to. But in the meantime, what we will see today, tomorrow, is that even in the presence of noise and in the absence of error correction, we can still do something out of these noisy systems, and we can do that very reliably. And that essentially is error mitigation. So if we think of error mitigation, and we can start by saying something like, say I have a quantum circuit. I have a quantum circuit here. It's a big unitary matrix, right? Any quantum circuit is mathematically a big unitary matrix, and you have all the qubits, you have all the outcomes. Now let's assume that the ideal outcome, let's assume this, that the ideal outcome, say it's a 5 qubit circuit, is say all 5 zeros. This is, if I run this circuit correctly, I should get all zeros. Now I run this twice on a quantum computer. Okay, so this is my run 1, this is my run 2. And on the first run, I get 1 0, sorry, 0 1 0 0 0. This is wrong. On the second run, I get 1 0 1 1 0. Fine. So let's call this phi. Let's call this phi 1. Let's call this phi 2. These two are the noisy outcomes, phi 1, phi 2. Now, if I ask you that, can you give some mathematical estimates on how these runs look like, how the outcomes of this run look like? One very well-known uh, one very well-known method or a very well-known metric is fidelity. So if I want to find, I can just check the overlap or the inner product between the two quantum states. What will happen if I take the inner product of psi and phi 1? Well, these are computational basis states, so they are orthogonal. I will get the outcome 0, because 0 0 0 0 0 and 0 1 0 0 0, these are two computational basis states. They are orthogonal with each other. So when I take the inner product, the outcome is 0, and I can take the mod square, doesn't matter, the outcome is 0. If I do the same with phi 2, again these two are computational states, and my outcome will be 0. But if I just ask you, forget about all these mathematical definitions and everything, fidelity, inner product, all of these are very big definitions. um, if I ask you that, see, these two are the outcomes, which one seems closer to the original outcome? You will immediately say this one, although this is wrong, but it is off by only 1 bit, whereas the second one is off by 3 bits. So the run 1 seems to be better than run 2. Now the question is, how do you estimate that? Because fidelity, if you do fidelity, it is going to give you that both of them are orthogonal, both of them are equally bad. But just by looking at it, we can kind of put some degree of badness, if you want, a degree of badness into this, and it seems that run 2 is way worse than run 1. How do we quantify this thing that we just like saw the bits and we kind of understand intuitively? How do we really quantify that? So to quantify that, we use, if I want to use quantum states, I have to eventually use fidelity, and that is not going to help. We just saw it is not going to help. So I need to come down to numbers. When I have numbers, so say if I have a corresponding number corresponding to these three, now I can say that, okay, the number corresponding to phi 1 is actually closer to psi. So it seems phi1 is better than phi2 in that sense. This is what we can say. So we need to go to a number from this quantum state. And this number that we need to go to is, we first need to define something called an observable. What is an observable? If you ask this question, maybe I will answer in a circular way and say anything that you can observe is an observable. What does that mean? So if I give you a quantum state, you can try to estimate many properties of that state. Say you want to find the energy of the state, you want to find, say, some momentum, angular momentum, many different things that you may want to find about the state. These are all numbers, right? Energy of a state is a number. Momentum, it will a number. Eventually you will get some values. Yeah, it's a vector, but you will get some values. So in order to get that, we need to mathematically assign something called an observable. An observable is a mathematical representation of the property that we are trying to observe. So let's call that O. And just like, it's a probabilistic method, right? If you run the circuit again and again, you are not guaranteed to get the same outcome because there is some probability associated with it. So if I think of, say, just a classical system, I toss a coin, I get heads with probability, say, zero 0.7 biased coin, and I get tails with probability 0.3. Something that we can, how can I use a single value to capture this information? Heads with probability 0.7, tails with probability 0.3. What we can do is something called an expectation value. So let's assign, say, +1 for heads and -1 for tails. Now I can say that, the expectation value that we get after the coin toss is +1 into 0.7 plus -1 into 0.3, that is 0.4. What it means, if you run this many times, and if you expect that, okay, say if we are playing this kind of game, if it is a head, you will give me 1 rupee, so it's my gain +1. If it is a tail, I will give you 1 rupee, so it's my loss -1. So if we play this game many times, ideally infinitely many times, then I am on average going to have 0.4. I mean, if I just divide, on average in every run, I am going to get a benefit of 0.4. That means you are going to lose 0.4. So this is kind of what an expectation value would mean, and we know this. This is coming from classical probability theory. So similarly, we can assign an expectation value for an observable, because it's a probabilistic state, and we are going to just run the circuit again and again, and we'll get different outcomes. So we need to get an expectation value out of that to take those information of those outcome into a single value or something that is defined as trace of O rho. This is the definition of expectation value, trace of O rho. One thing that you can very easily do, let's take a pure state. You can show the same for a mixed state also. But let's take a pure state. Then my rho is of the form psi. So trace of O rho is equal to trace of O psi. Now trace has a cyclic property. What it means is trace of ABC is equal to trace of CAB is equal to trace of BCA. So it's as if you can rotate and the trace remains the same. Trace has this cyclic property. So I'll use the cyclic property, and here you get trace of psi O psi. So I have taken this to the front, trace of psi O psi. Now see, expectation value is a number, right? So shy O shy, if you do that, what is it doing? O is an observable, it's an operator which is acting on shy, and then you are taking an inner product of them. It will become a number, right? This O acting on shy, it will create, say, let's call this trace of shy O. Let's say O acting on shy gives us shy O. Now this is an inner product. So that's a number. What is the trace of a number? It's just that number itself. So I'll just go back to this notation. You can show that it is shy O shy. Fine. So either you go for trace of O row, or just for pure state, you can write it as shy O shy. I'll just definitely encourage you to go back and do the same calculation for a mixed state and see what happens. Okay, second thing, an observable needs to be a Hermitian operator. So an observable O is a Hermitian operator. In case anyone don't remember, so just for the sake of completeness, a Hermitian operator is an operator which is its own complex conjugate. So it's a Hermitian operator. Okay, there is one question that the probability when a coin is tossed will be half. Yeah, I was just talking of a biased coin here. Just to show you, if it is a fair coin, then you are right, it will be 0.5, 0.5, then the expectation value will be 0. It's 0.5 minus 0.5, 0. So depending on the probability, your expectation values will change. So it's a Hermitian operator. Now, any Hermitian operator, in fact, you can do this for any unitary operator. Hermitian is a very special, I mean, it's something more on top of unitary operator. So you can write down your observable in terms of Pauli gates. Okay, how the combination 0.7 and 0.3, this I have just taken as an example. That it's a biased coin, and the head comes with probability 0.7, tail comes with probability 0.3. This is just, I have taken this example, just an example. So you can write down, if it is a single qubit observable, just for, let's say it's a single qubit observable for now, you can always write down as a linear combination of the Pauli operators. These coefficients we need to find. For the when an observable is given, we need to find these coefficients. In general, if it is just a one qubit, then these are on I, X, Y, Z. If it is an n qubit, then you have all the Pauli terms, n qubit Pauli terms. In that case, we just generally write this as sum over CP P, where P's are the n qubit Paulis. So what it means here is that if you want to calculate psi O psi, you can write it as psi sum over P CP P psi. So that would mean sum over P CP psi P psi. So what we need to do? What we need to do is we need to calculate these terms on a quantum computer. These terms we will calculate on a quantum computer. These are again numbers. Once we get these numbers from quantum computers, we can just do this multiplication with CP and then adding all the terms classically. So this part, multiplying with the coefficient and then adding all the terms together, this is done classically. Fine. I hope this is clear. Now the question is, how many quantum circuits do I need to calculate this psi O psi? In general, it seems that you have to write down what are the different p terms. For example, let's say you can have an observable which is, say, zero point 0.2i plus 0.8x. There may not be y or z terms. That means the coefficients of y and z are zero. We can have something like this. So it is not necessary that when you go to an n qubit Pauli, you have all possible 4 to the power n p's here. How many Paulis will be there? 4 to the power n for n qubit things. So it is not necessary that this is actually a 4 to the power n terms. Many of the coefficients can be zero. So we can have a way simpler Pauli. Yeah, in the worst case, there can be 4 to the power n terms. So in general, it will seem that each of these will need a quantum circuit. So one quantum circuit for each. That means now what it means is you will need to run many quantum circuits. From each of the quantum circuit, you will calculate this term and then multiply and add. But we can do better. So we can do better. Let's ask how. So the first question is, let's try to take a simple case. I am just starting with the state 0 and I am measuring. Fine. I want to calculate the expectation value of, say, 0.2i, or just let's not take I, because I and z will be the same. So let's take 0.2z plus 0.8x. Fine. We will talk about doing better in just some time. But yeah, this is important. So I need to calculate I need to calculate 0.2 psi z psi plus zero point 0.8 psi x psi. I need to calculate this part using a quantum computer and this part using a quantum computer. Now see what it means. This part, this first thing, it means you need to measure on in z basis. This means you need to measure in x basis. Now there is no quantum computer at this point who can measure in x basis. Quantum computers only measure in z basis. So the first term is not a problem. We'll take 0 and we will just measure it. Or measurement is always in z basis. So what we need to do, we cannot measure in x basis. Does that mean that, okay, we cannot do this thing here? No, we can always do this by a change of basis. So first let's do this mathematically. Let's take look into this part. We have psi x psi. Now, how many of you are aware of this equality? If you are not, once more go and try out and see that this works. Is equal to HZH. Since this equality holds, we can just write this is equal to H psi psi, and this is essentially, let's call this psi h, z psi h, right? And once we can calculate psi h, we can calculate this, because then it needs a measurement in z basis. How do we calculate this? How do we find this psi h? That is also very simple. All it is saying is apply Hadamard gate on the quantum state. So I need first circuit, which we have already drawn. I need a second circuit where I first apply a Hadamard gate and then measure in Z basis. These two together is measurement in X basis. So this together is X basis. Similarly, if you want to measure on Y basis, you have to do a Hadamard and an S gate. 2 extra gates are required. So you can actually, even though we cannot measure outside Z basis, you can actually convert any other basis that you need. That will be Pauli. So you can just take that gate and you can convert it into Z basis measurement. Let's come to a 2-qubit system. Fine, so this is actually easy. Now what we will do is we will measure this multiple times, and I'll first measure this circuit and I will calculate this term from the first circuit. Then I will measure this circuit, I'll calculate this term from the second circuit, and just multiply by 0.2 and 0.8 and add them. This will give me the expectation value for the observable O, which is this 0.2z plus 0.8x. Yeah, okay, so Y basis you need S and H. For Y basis you will need both S gate and H gate. Just like for X basis you needed H gate, for Y basis you need S gate and X gate. H gate. S gate and H gate. Let's come to a 2-qubit observable. So I have my observable now. Let's call it 0.2 Zi plus 0.3 ZZ plus 0.4 IX plus 0.8 ZX plus say 0.8 XX. Just an example, observable. How many circuits do we need? Ideally 4 circuits at this point. What will be the circuits? So I will have my first circuit. See, measurement in Z basis and I basis is essentially the same. So this will be my first circuit. What do we have to do if we measure in Z basis, and what we will have to do if we measure in I basis? So again, if you are not aware of this, I'll again encourage you to go back and write, just try this out. Z is 0, 0, minus 1, 1, whereas I is 0, 0, plus 1, 1. Yeah, I mean, if this is really new to you, I really request you to please go and just do and see that if you calculate this 0, 0, minus 1, 1, it gives you the matrix for the Z basis. If you do 0, 0, plus 1, 1, it gives you the matrix of the I, not basis, the I gate. Just try this out, because this actually clears our concepts a lot. So when I want to calculate Z, what can I do? I can check, I can take the circuit, I can check, I can measure it many, many times. I will see how many times I am getting 0. I will see how many times I am getting 1. So the expectation value corresponding to Z will be number of times I am getting 0 probability minus probability I am getting 1. And similarly, if I want to calculate I, it will be probability I am getting 0 plus probability I am getting 1, which is always equal to 1. This is always equal to 1. So that's why Z basis and I basis, both of them basically requires this probability of 0 and probability of 1. If it is only I basis, we don't really even need to do anything. We know it will always add up to 1. So both of them are actually measuring in the same basis. We don't need any change of basis for this. So this will give me my Zi term. Second, I have Zx. So for Z, I need this. For X, I need Hadamard followed by measurement. This is what we saw before. This will give me Zx. Fine. For Ix, I will again just measure. Then I take this. This will give me Ix. And this will give me Xx. Right? So I hope this is clear to you all, that how we can just calculate each and every term. Now let's come to this point. We can do better. Because then you will be thinking, otherwise what you will be thinking is that, oh, now if you take this to a 100 qubit system and then you have say 100 or 200 terms, you will need 100 200 circuit executions. Not necessarily. We can do better. How? Let's look into this first and second case. Just let's look into this first case and this second case. We will look into third and fourth later. Let's look into this and this. What we just discussed is, when we have this I gate, we don't really need to do anything. We know that the expectation coming out of the I is probability of 0 plus 1. That means it is 1. I don't really need to do anything. So if I replace this measurement, and if I say I'll put it on Hadamard gate and measure, that means I am going to measure this on X basis. Does it matter? What will happen if I measure on X basis? Then what I will get is probability of plus, because Hadamard, it takes 0 to plus and minus. Now when we measure, I'll get plus or minus, right? So it is probability of plus plus probability of minus, which is again equal to 1. So it doesn't really matter whether I am measuring this in Z basis or X basis. When it is I, right? It doesn't matter. So now if you see, if I just replace this with this Hadamard and measurement and say I'm going to measure my second qubit in X basis, then this circuit, and this circuit becomes the same. So I can just use a single circuit and I can calculate 3 values at once. Fine. We will go a bit deeper into this. So don't worry if you still have questions, but just see that what we have just discussed is clear. The only change that I did here is I said that it doesn't matter if I measure in X basis, Y basis, Z basis when you are talking of identity. Because we know it is always going to be 1. Measure in any basis you want, it is going to be 1. The ideal expectation value. I don't even need to run a quantum circuit for that. And the moment I said that, I can replace this measurement in Z basis with this X basis measurement, and I end up with 3 same circuits. So now I can run this circuit only once. So instead of 4 circuit, now I need only 2 circuit. One circuit for this, and this is a separate circuit. So this is a second circuit that we need. Now, the next question that you might be having in your mind is that, okay, something, I mean, you just showed this, it's a 2 qubit system. So it's very easy to see and do this. Again, what if it's a 100 qubit system? What if it's a 50 qubit system? How do you really identify that you can replace this with this kind of measurement and you can take these 3 terms together? How did you identify that? It cannot be manually looking at the circuits. Then you cannot scale this thing up for bigger systems. So here comes the idea of commutation. You know that when two observables don't commute, then we cannot measure them simultaneously. So what it means is that if I have two observables, say position and momentum, we know that these two don't commute. We have the Heisenberg uncertainty principle and everything. If these two don't commute with each other, what it means is, if I measure position first, it will affect momentum. So after measuring position, if I measure momentum, I will get some value of momentum. On the other hand, if I measure momentum first, then measure position, I'll get a different value of momentum. So in the first case, I'll get a correct value of position, which will affect the value of momentum. I'll get an incorrect value out of momentum. And in the second case, when I measure momentum first, I'll get the correct value of momentum, which will hamper position. I'll get some incorrect value of position. But if these two operators commute with each other, if I have two operators which commute with each other, then this problem does not arise. Two operators which commute with each other, it doesn't matter whether you measure operator 1 first or operator 2 first. And it's very easy to mathematically see that. Say I want to calculate some O1, O2 psi, and O1 and O2 will commute with each other. That means I can simply write this is O2, O1 psi. These two are equal. So O1, O2 is equal to O2, O1. That means I can just do this, and if it helps me to calculate O1 first, I'll do that. This I can do. So similarly, what we need to do is we need to find qubit-wise commutators. And if we look into qubit-wise commutators, see the first three qubits here are Z or I. They commute with each other. X doesn't commute with it. So I cannot take this together with the first circuit, even though if you look into the second qubit, this, and this, all four of them commute. But when I look into commutation, every qubit should individually commute. So in this first three cases, Z, Z, I, they all commute with each other. In the second qubit, I, X, X, they all commute with each other. So I can group these three together. On the other hand, here XX, although the second qubit commutes with every other terms, the first qubit doesn't. So I need a separate group for that. So here that this is how we will create a partitioning of the observable terms, and each of these partition will require its own qubit or own circuit. In the worst case, we will require a circuit for each of the terms, but in general, we can actually do this kind of commutator calculation, and we can actually reduce the number of circuits significantly. And in particular, when we go to Qiskit, perhaps you have seen, and you should, I don't know whether you asked this question to any of the speakers who showed you or to yourself. In Qiskit runtime, we have two primitives. One is the sampler, which gives the probability distribution. Other is the estimator, which gives you expectation value. I'm sure you have seen this in some of the Qiskit lessons or something. What you should ask yourself, and you know the answer now in some sense, how did we calculate the expectation value? Like this is how we calculate expectation value, right? How did we do that? We get the probability distribution, and then we do some classical calculation on top of that. So if that is the case, why do you need two primitives? You could just take the sampler, you get the probability distribution, and then do some classical calculations on top of it, and you get the expectation value. So why do you need a separate primitive for calculating expectation value? And in fact you can do that using sampler. You can get the probability distribution, and there is a function that is called sampled expectation value. I mean, you can write your own function as well. It's very easy, but there already exists a function which is called sampled expectation value, and you can pass it the count dictionary that Qiskit returns, and the observable, and sampled expectation value will just do the classical calculation and return it to you. So this is how we can calculate expectation value. And in fact, in fact you can write your own function as well. It's very easy, but there already exists a function which is called sampled expectation value, and you can pass it the count dictionary that the Qiskit returns, and the observable, and sampled expectation value will just do the classical calculation and return it to you. Why we need an estimator is to do this kind of partitioning. Yeah, right. Sampler is a primitive. It's not really similar to air distribution. So air simulator is one of the simulators that we have. You can pass in any backend you want to sampler. It can be an ideal air simulator. It can be a noisy air simulator, or it can even be a real backend. What estimator does is, if you go and see estimator, the main work that it does is this partitioning. It runs some tree type algorithm, because you can understand that if you have many terms, then here also doing this partitioning is not a very easy problem. So what estimator does is some tree type search, and it will do the partitioning very efficiently. It will find out what circuit you need for each partition, and it will find out which basis you need to measure for each partition. Like in this case, if you only take the first term, you don't need this Hadamard in front of measurement. But if you are taking this entire group together, then you need this Hadamard here. So these are the things that estimator does, and after that it's just doing what sampler does. But creating, first doing the partitioning properly, second finding out which qubit needs to be measured in which type of basis, and then third creating all the circuits for each of the bases. This is what the special thing that estimator does. Once it does that, then you can just run, get the probability distribution, and then again classically calculate the expectation value. Why did I spend so much time talking of expectation values here? Because when we come to error mitigation, you see, when expectation value, remember how we started. This one seems to be better than this one. This is how we started. Expectation value gives us a number. The moment we have number, we can move away from fidelity, and we can say this number seems is closer to that number. This number is closer to the ideal number. And this is what error mitigation does. It starts with a number, an expectation value, which is, say, ideally far away from the ideal expectation value because of noise. Then we take that expectation, then we do some calculations on top of it, say some quantum overhead as well as classical overhead. We do those kind of overheads on top of this, and then we go and just find another expectation value which is closer to the ideal. This is what mitigation does. In just one sentence, if you ask what is mitigation, it looks into noisy expectation value, it does some overhead, both classical and quantum. We will see what those overheads are, and then it gives you the and another expectation value which is closer to the ideal. This is what error mitigation does. So error mitigation is acceptable only when you have expectation values. Any problems where, so let's try to just think of problems where expectation value is not useful. Quantum communication, if I am sending you bits, zeros, ones, or something, if I am sending you a message, you want to retrieve that message, you don't want to calculate some expectation value of that message. That makes no sense. So quantum communication, I don't need an expectation value, I need bit strings, what you send. Say Shor algorithm, when I am giving you a prime number and you want to factorize, you want to know the two prime factors, not some like linear combination of the two factors. When you are using Grover's algorithm, you want to know the exact look thing that you were searching for. Where is that thing that you were searching for? You don't want some function of that thing. So these kind of algorithms which we study in the beginning of quantum computing, Shor algorithm, Grover's algorithm, say quantum phase estimation, these kind of algorithms require the final state of the system. Quantum communication, in many cases quantum cryptography, they require the final state outcome. They need the psi, they need the final psi, or they need the probability distribution. Error mitigation is not useful in that case. But there are again many problems. Say you are doing a chemistry problem, you want to find the ground state energy of a molecule. It's a number, it's an expectation value. Say you can create an observable which will be the Hamiltonian for the system. So the eigenvalue of the observable will give you the energy of that system. It's a number. If you are looking for, say, physics problems, many physics problems, I am say I start with some systems and there is a Hamiltonian which drives the system. At the end of the at the end of the case, I want to know some properties of the system. If you can if you can represent that property as a number, it's an expectation value. If you have optimization problem, I want to know some graph properties. I want to know what is the cut size of this graph. I want to know, I have given a color. I want to know, like, how good is this color? I mean, how many edges had different colors? These are all numbers. You can create observable for those problems, and you can calculate expectation value. Machine learning, eventually you want some F1 score or some accuracy. This is what you want to improve over and over the time. So this can be cast as a number and expectation value. So all these problems that I just talked about, I just told you that there are many problems which don't fit into this model that I am talking of, that you need to calculate expectation value. On the other hand, there are many problems which does fit into this model where you want to calculate expectation values. So what we will see about error mitigation is useful for this set of models, like chemistry problems, physics problems, some physics problems, say optimization problems, machine learning problems. These are the problems which we can tackle using error mitigation. We can get some improved result out of the noise. Okay, so I think we are over just 1 hour. If you want to take a break, we can just take a break and then come back with specific examples of error mitigation.
So participants, we may have a break of 5 minutes. Uh, Meanwhile, you can also go through what Sarab has taught till now. Just summarize it, and if you find any concept that needs to be discussed, just put it in the chat box.
Yeah, sure. Okay, let's take a 5 minutes break and then come back.
Few questions are there, sir. After rejoining, we may address those questions, sir.
Okay, these questions I already addressed, this probability kind of thing. These questions I already addressed. Are there
Okay,
more?
okay. Then it's fine, sir. Okay, sir.
Okay, awesome. Yeah, let's take a 5 minutes break and maybe come back at 4:10 or something.
Sure, sir.
Okay. Hello. Should we get started?
Yes, yes, sir.
Okay. I hope this is, yeah, visible. Okay. Let's get started with error mitigation. Now we kind of understand expectation values, how to calculate them, and how we can efficiently calculate them, what an estimator does, why an estimator is required even when we have a sampler. Um, we understand where error mitigation is works and where error mitigation doesn't work, right? So let's get started and try to understand some error mitigation protocols now. So we will look into all of these, if maybe not by today, but we will also take this to tomorrow. So we don't need to uh, complete everything today. The goal will be more to understand each and every step as we go ahead. Of course, you can go back and learn more things about this, but my goal here will be to give you a story of the steps and why the things are as they are. So let's get started, and we already did this thing, that what a quantum computer can do and how do we calculate expectation values. We did this in quite a lot of details. Now, what we want to do is, as we said, that we want to calculate expectation values. So we have a circuit and we want to calculate expectation values. How do we do that? We measure the circuit, we get the outcomes. So if you don't know, great. If you don't know, don't worry. This is something called a GHZ circuit, which is kind of a generalization of Bell circuit for higher number of qubits. And as you can see, just like in Bell state, this Hadamard and C naught, just like in Bell state, we have 0, 0 and 1, 1 as the outcomes. Here we have this all 0 and all 1 with equal probability. And when we calculate the expectation value of some observable, it is calculated as trace of O rho. This is what we saw. Now, this also, we kind of argued that none of the things that we do on a quantum computer are perfect. So each of the gates are noisy. When a system remains idle, it has a tendency to decohere, release extra energy, and go away to the ground state. Then when we measure, the measurement themselves are not correct. So if we run a system, a circuit like this, although the ideal outcome should have been all 0 or all 1, here, because of the presence of noise, we will end up getting some other states also with low probability. Ideally, we hope that the noise comes with a very low probability. So we will get other states with low probability, but we will get something beyond what we expect. That's what noise will do. So if we calculate the expectation value now, see this part. So this part will give trace of O rho. These two are correct outcomes, trace of O rho. But we will also have something coming out of these other states, some things that these states will contribute, some contributions coming out of these states. And these are unwanted contributions, which we call as this beta bias. So we want to calculate this trace of O rho. We end up calculating trace of O rho with some bias or some noise. So if we look, this is the one of the current IBM quantum systems that we have today. This is a 156 qubit Heron processor, and in particular, this is IBM Pittsburgh. Um, these are the physical qubits, and whenever there is an edge between two physical qubits, what it means is that you can do a 2 qubit operation between these two. Now here, if you see that all the information that you are getting here, they give you all the different noise information that you have. So this is the readout error. So as we talked about, that measurement is also not perfect. We have some imperfection in the measurement as well. And here you can see that what is the probability of imperfection in each measurement. Two things to keep in mind. First, measurement is imperfect. Second, the imperfection is not uniform. So you see that there are many qubits which have suddenly very high readout error. So if you see, this is kind of the median value of readout, and then suddenly we have some of the qubits which are pretty high than the median value. So two things. First, they are noisy. Second, noise is not uniform. Similarly, if you have H error rate is the Hadamard error rate, but it is essentially showing you any single qubit error rate. And here also, if you see, we have two things. First is we have noise, and noise is not uniform. This color code shows you how noise is distributed. Same goes for two qubit operation, C naught. The same goes for that. Now let's see two things here, basically three things. First, we were saying there is two qubit noise. So you can see that these two qubit operations, the edges, they are also color coded, and the color code tells us the noise. So for example, this two qubit operation is very noisy. This is better. So once more, noise is not homogeneous, it's very heterogeneous. And the second thing is here, the noise, the probability of noise you can think is almost 100 times than single qubit gates. This will come handy later on. So keep this in mind, that the probability of error in C0 gates is almost 100 times the probability of error in single qubit gates. So these are the few things. Now, what we want to go towards error correction, and that is going to happen very soon in 2029 and beyond. We are going to get error correction. What is the idea of error correction? You have to detect the presence of error. You have to somehow understand what type of error has happened, and then you go ahead and correct it. This is what error correction is. And if you can do it in a fault tolerant manner, you can suppress errors to arbitrary low levels. And this is kind of the eventual goal that we all have, that I want to suppress error to as much extent as we want. But this has some drawbacks of its own, that it requires a large number of qubit and hardware overhead. So if you look into, say, a surface code, you need roughly 17 qubits to encode a single qubit by doing error correction. So you can understand the overhead that it comes, and then when you have to do it fault tolerantly, the overhead grows exponentially, and all of those things are here. But eventually, this is definitely the goal, but this has its own drawback. What we have today is mitigation and suppression. Now, you don't have to be very aware of the difference between mitigation and suppression. These are less mathematical differentiation than, I would say, differentiation made by IBM for certain reasons, and you will see what are the reasons. So that's why it's not very important that you look into something and be able to identify whether it's mitigation or suppression. That's not required really. First is, let's go to suppression. Errors are suppressed but never detected. So this can, I'll give you an example of how this can happen. You don't have to detect error. You don't have to understand what type of error has occurred. You can even suppress the effect of error before that. Okay, just hold on to an example of that. It can extend the lifetime of quantum computation. Of course, if you can reduce the effect of error, this will improve your computation, but you cannot expect that this will give you arbitrarily low error level, something that error correction can give. But and the interesting thing is, there is no extra qubit requirement, no increased runtime. Example. So what we saw here is that this qubit is very noisy, this is not. So when you are transpiling your circuit, if you are given a choice between 105 and 117, which one will you choose? Of course 105, right? Because from the information, the backend information, you know that 117 is more noisy. So you don't even wait for it to create any noise. You will say, if I have the option, I am not going to use 117. Similarly, 2 qubit gates, if I have the option of using 10396 instead, I am not going to use 9683. So these are kind of pre-processings, and the other thing that we have is dynamical decoupling. We will see later. twirling, again we will see later. These are the things for which you don't have to run any extra circuit, you don't need any extra qubits, but you can still suppress the effect of noise. Mitigation, kind of similar here. It cannot go to arbitrary low level. Again, errors are modeled and removed. Here, errors are suppressed even before detecting. Like you don't even allow it to go for an error. You just avoid 117. But here you make some modeling of the error and remove as a post-processing step. You don't need any extra qubits. Like here I said you need 17 qubits to encode a single qubit in a surface code. That is not required here, but runtime increase definitely happens. Here there is no extra hardware runtime also. You just choose not to use this. There is no quantum overhead of that. But here there will be quantum overhead. This is kind of the main difference between mitigation and suppression. But again, it's good to know, it's not necessary to understand or be able to see some method and identify it as a mitigation or suppression. So if we try to think of the different types of noise, of course, there are way more noise and more types of noise than what I have written down here. But very generally speaking, we have depolarizing noise. So here the system kind of goes towards a completely mixed state, which is essentially just like a coin toss. So you lose any information. It's totally randomness that happens. You have coherent over rotation. So that this means that I am asking you that okay, you need to implement this unitary, which is a rotation by theta. You end up doing theta plus delta theta, so this extra over rotation that comes here. Then you have T1, T2. So T1 and T2, T1 we kind of, it's kind of saying that, okay, if you put a system in an excited state, it will die down. It will spontaneously release the energy and it will come down to the ground state. And the time of this release of energy, kind of a half-life, like radioactivity half-life, that half-life is given by T1. It's a hardware characterization. Each hardware will have a different T1. Similarly, if you create a superposition state and leave it idle, it tends to end up acquiring some extra phase that you don't want. And the speed of acquiring is kind of denoted by T2, which is again a hardware characteristics. Crosstalk, it is very easy to understand. Like if in a class, say every student starts speaking with the next student, however in low voice, if people start doing that, suddenly like the class will become messy and noisy, you cannot understand anything. So crosstalk will be something like this, that say I am doing a C0 operation between these two and these two, but this qubit is affecting this qubit and now things get messed up. So something like that is crosstalk. And we have state preparation and measurement error. Like we said that, can you prepare a state properly in zero? Prepare a qubit in zero properly? The answer is no. Can you measure properly? The answer is no. But the interesting thing is that these two cannot be really uh, identified uniquely. Like if you prepare a state and you measure, you get, there is no gate operation or nothing. Let's assume no gate operation, nothing. You prepare a state and you measure. So you should be getting the outcome zero. Now say you measure 1,000 times, you get 0 900 times, 10 times, you get outcome one. How do you say whether it was because those 10 times the qubit was prepared wrong, or it was measured wrong, or both? Like sometimes the qubit was prepared wrong, sometimes it was measured wrong. There is no way to identify between these two. So these two are taken together and called state preparation and measurement together and spam. Again, many other things are there, like leakage. For example, leakage, we say alpha 0 plus beta 1. But any quantum system inherently is infinite dimensional. So we are just restricting ourselves to those lower two states. But sometimes when we start doing computation, the energy actually goes to the higher state. This is called leaking away from the computational basis. So all those type of things are there, but the type of errors that we will deal with mitigation are mostly these. Now, Even though I say there are more types of errors, but as you can see that, okay, I have already written down a set of many errors. And if you have so many types of errors, there cannot be a single way to deal with all of these. And that's what we are going to look into. We have measurement error mitigation for span error. For these kind of T2 crosstalk, even T1, we have dynamical decoupling. Then we have something called twirling. And then we have what we kind of say as error mitigation techniques like this zero noise extrapolation, probabilistic error amplification, and so on. What we will do today is start from today and tomorrow, is start from the end and slowly move inwards. We will start with some assumptions about the system and we will see this works, and then we will try to see that, okay, that was a assumption. What happens if you remove that assumption? What more do you need? And slowly we will start moving inside. This will be the plan. So let's start with zero noise extrapolation. The idea of zero noise extrapolation is like super duper simple. And it is as so simple, sometimes I feel like that, oh, I should have been the one inventing this. But anyway, let's start with the idea and we will see examples. First, the idea is that if you have a quantum circuit, the hardware is noisy. So when you run the circuit, there will be some noise associated with the circuit. It is parameterized by some lambda 1. And you are not allowed to ask this question that how do you get the value of lambda 1? What does lambda 1 physically mean? How do you even parameterize lambda 1? You showed so many noise. Which one of them is lambda 1? If not, how do you combine these noise? None of these questions I am going to answer at this point. And you will see very soon that you don't need these questions answered. You just need to think that this is a mathematical value which kind of captures the noise in the circuit. That's all. Now I create a set of noise factors. Say lambda 1 we already have, then we have lambda 2, lambda 3 in an increasing order. Like lambda 2 is greater than lambda 1, lambda 3 is greater than lambda 2. And for each of the case we have a circuit. The only requirement is that each of these circuits should be functionally equivalent, but the noise on this circuit, the second circuit noise is more. Third circuit noise is even more. Once more, at this moment, you are not allowed to ask how do you create this. We will see that, but let's assume that it is doable. The circuits are functionally equivalent, but the noise acting on the circuit are different. Now, if we can do that, we can just run those circuits and calculate expectation values for a given observable. For each of this noise factor, these are called noise factors. So for each of these noise factors, we can calculate expectation value. Now, if you look into this, what happens? You have, say, three noise factors, lambda 1, lambda 2, lambda 3. Corresponding to those, when you run the circuit, you get some expectation values, and the expectation values will start becoming worse and worse because I'm saying these circuits, although they are functionally equivalent to the original circuit, they have higher noise. So if the noise is higher, the result will be worse. So they are moving away and away from the ideal result. But the moment we do this, we select a few noise factors, we calculate the expectation values. You see now what happens, we have a few data points. Now we can just fit the data point with a curve and extrapolate it. When we extrapolate, this value gives us an estimate of the ideal expectation value in the absence of noise. So let's think of this like critically one or two things. First, we take say three noise factors. So we now have to run three circuits, not one. So remember when we said that in error mitigation, you have no extra qubits but increased runtime. So it is kind of the same circuit. I'm saying they are functionally equivalent that you are running, but they have more noise. But now you are running the circuit three times. So if you're running the circuit three times, the overhead is three times. This is point one. Point two, I am fitting a curve and then I am extrapolating it. So I'm saying this because I have seen people claim something like this, that error mitigation removes the noise from the system. This is completely wrong. Error mitigation cannot remove noise from the system. What it does is it gives you an estimate of what your expectation value would have looked like if there were no noise in the system. These two are very, very different. It's getting an estimate of what the thing looked like if there were no noise. This is not the same as removing the noise from the system. So it doesn't remove the noise from the system, but it gives an estimate of the zero noise scenario. Now this comes with an assumption that the nature of the noise remains same with increasing lambda, and I'm not going to talk about this a lot. Maybe not today, we will see depending on the time. But definitely not right now. I am not going to talk about the nature of noise. Now we want to address a few things. Let's ask that, okay, how do you create these circuits which are functionally equivalent, but they have like different noise? How do you do that? And it's very simple. The first zero noise extrapolation paper that came out, J. Gambetta and others, they proposed something called analog ZNE. You know, each of these gates eventually boil down to some pulse. What was done there was something called pulse stretching. You can stretch the pulse in such a way that though the two pulses remain equivalent, but when you stretch the pulse, that means the pulse occurs for a longer time, it will naturally have more noise. But the problem in this approach is that the user needs to have knowledge at the pulse level to implement this. Rather, digital zero noise extrapolation is way better. What it does is, you know, every gate is a unitary matrix. If it is a unitary matrix, it has an inverse. That is the definition of unitary matrix, that the complex conjugate, the dagger of the matrix, is its own inverse. So if I take this gate and if I replace U with U dagger U, see U dagger U is identity by definition of unitary matrix. That means these two scenarios are equivalent. If I just have U as a single gate, or I have U dagger U, I have three gates, but these two are doing functionally the same thing because this is actually identity. It is not doing anything more. You can understand I could have replaced this with say 5 times, 7 times. I can replace this with any k. It doesn't change the functionality of the circuit. So if this were an ideal scenario, running this circuit and this circuit will give me exactly the same result. But it's not an ideal scenario. So we are not going to go too much into this mathematics. It is not an ideal scenario. Each of these gates come with some noise. So when you repeat one gate 3 times, the noise is in general increased by 3 folds. If you replace this by 5 times, the noise will be increased 5 folds. If you replace this with k times, the noise will be increased k folds, right? And if you consider a depolarizing kind of noise here, don't worry if this is not immediately very clear. You don't really need to worry. What happens is a depolarizing noise or a stochastic Pauli noise channel has a structure like this. With probability 1 minus p, the density matrix remains unchanged. And with probability px and x gate is applied, with py, y gate is applied, pz, z gate is applied. These are noise. This x, y, z, these are noise. And like these are unwanted. I was not wanting these. If px is equal to py equal to pz, then we end up getting what is called a depolarizing noise model. And if we have more gates, so if you have a single gate, probability that the gate fails is 1 minus p. If you have two gates, probability that the gate fails is 1 minus p square, 1 minus p cube, and so on. If you have k gates, the probability of getting the correct density matrix goes down exponentially, right? It goes down exponentially. So if you have k of those, then the probability of correct outcome is 1 minus p to the power k. I don't care what happens here at this point. The probability that I get the correct outcome will become 1 minus p to the power k. So it goes down exponentially. Now, we need to choose an extrapolator. So we said that here first you prepare some noise factors, you run the circuit. We understood how to get the noise factors, like how do we create the functionally equivalent circuits and with increased noise, that we understood. The other thing that we need is that you need to fit a curve. How do you fit a curve here? So for that, 1 minus p to the power k is exponential. So you can just fit an exponential curve, right? Always. But in practice, so here is theory versus practice. Theoretically speaking, this is an exponential curve. Things are going down exponentially. So you should be using an exponential curve to fit the data points. But in practice, often what is seen is that exponential fitting is very unstable. You will end up getting like very diverged values if you use exponential fitting, most of the cases, not always. So what is often done in practice is that we want to fit some other type of curves. Like we don't just want our result to blow up, just diverge away. So if your P and K are small, that means your circuit is small. You can do a Taylor series expansion and it will go like this. So if your P and K are small, then you can say this order of P square or order of K square. These are like very small and negligible. So it becomes a linear fit. If your system is slightly bigger, and you can say that no, I cannot anymore say that p square is negligibly small, p square needs to be taken into consideration, then you do an Taylor series expansion and you kind of throw away higher terms, cubic or higher terms, and then you can do a quadratic fit. So if you go to Qiskit at this moment, it will allow you to do linear fit. They call it polynomial fit, and you can choose the degree. So quadratic is polynomial degree 2. You can have cubic, which is polynomial degree 3. That means you take up to 3 powers, and from the fourth power you ignore. I think you can go up to polynomial degree 4 or 5, and then you can go for exponential. So this is how you fold the gates, and this is how you select your extrapolator. Now there are, so this is, if you think this is the entire story of zero noise extrapolation. And now perhaps you understand why I was saying that this is like super easy and intuitive to understand what is going on. But there are some good practices which are good to know. These are practical things that are done. I hope you remember that I kind of emphasized that the probability of noise in 2-qubit gates is 100 times more than single qubit gates. So in general, if you do zero noise extrapolation in qubit, the practice is that I am going to leave the single qubit gates. Here I have folded each of the gates. This is called folding, gate folding. Here I have folded each of the gate, and this is increasing the depth by 3 times. If I do it 5, it will increase by 5 times. One of the practice is to say that, okay, the probability of error of this is 100 times more. So by all means, we can say compared to this, these two gates are almost perfect compared to this. With that saying, what you can do is you can just say that I don't need to fold these gates. I need to fold this one. This is where the noise is coming from. So I will just fold this one, not this one and this one. This is the good practice that is done in Qiskit, but you can even ask Qiskit that no, I need to fold the entire circuit. The Qiskit will do that. There is a second thing, just since we are going into detail of ZME, this is called local folding. That is, you locally fold each of the gate. There is something called global folding, where you consider that this is my entire circuit. This is a U. So I will now put U dagger, which will be the inverse of the entire circuit, and then I will put back the entire circuit again. So instead of folding each gate, it takes the entire circuit, puts an inverse of that circuit, then puts that circuit again. That is called global folding. And what is often observed is that if your um, if your noise is non-Markovian, then global folding is better than local folding. But most of the times in quantum computers, what we observe is that Markovian noise is more dominant than non-Markovian noise. So usually, again, Qiskit allows you to do global folding, but in general, it will not do global folding for you. Second thing, we want to go to bigger circuits, right? I mean, this is just a 3-qubit circuit, just an example. But ideally, we want to go to a circuit of, say, 100 qubits, a lot of depth, thousands of gates, and everything. Now, in that case, let's say that the 2-qubit depth of my circuit is 20. It's not very high. It's a very, like, I would say 2-qubit depth of 20 right now is a very small circuit. It's super small circuit at this point. We can go up to nearly 2-qubit depth of 100. So it's a small circuit, not even a medium circuit. But if I fold it with lambda equal to 5, okay, just one thing, just for the sake of completeness, what is 2-qubit depth? When we calculate depth of a circuit, we start from the beginning, we look into the timestamps. So 1 timestamp, 2 timestamp, 3 timestamp. Depth of the circuit is 3. Even if we have another gate here, this gate and this gate will act parallelly. So they will contribute to 1 timestamp, 1 depth. So here, depth of the circuit is 3. 2-qubit depth means you throw away the single qubit gates, just ignore them and calculate that, okay, 2-qubit depth here is 1. Why is this useful? Again, because the noise coming from this gate is way higher than the noise coming from these gates. So knowing the 2-qubit depth, whenever you are going to do your own experiments after this, knowing the 2-qubit depth gives us more information than knowing the depth of the circuit. Like if you want some help from me, the first thing maybe I'll ask is how many number of qubits and what is the 2-qubit depth, not the depth of the circuit. So now we have, say, a 2-qubit depth of 20 and we fold with lambda equal to 5. So each gate is replaced 5 times. Now the depth of the folded circuit becomes 100. So often what it can happen is, right now I think the Heron processors can handle, this is kind of pushing it to the limit. But if you take 30 here and say lambda equal to 5, 150, most likely what will happen is that this circuit is too deep and you will just get some white noise. It will just become a random system. There will be no signal left. So if the expectation value that you are getting is a completely random signal that has nothing to do with the original circuit, then your extrapolation is not reliable, right? So what we need here is, I need some information of the circuit to remain here. I need to see how the circuit's outcome is getting worse. If this is a complete white noise, then this information is, then this fitting is wrong because this has nothing to do with the circuit. It's just a random white noise, right? So what we need to do here is then, by doing zero noise extrapolation, I cannot take it to a very deep circuit because 30 I am saying is a very mediocre range, small range circuit, and then I am saying that you cannot do lambda equal to 5. So how do you do? I mean, this is 3. The step after this is 5. So if you can't even do 5, then how do you really go for bigger circuits? The solution is partial folding. That's why I was so precise in saying that I am not going to define lambda as any physical information. Now I will say lambda is equal to 0.2. What it will mean is that you take lambda equal to 0.2. So you take 10 gates and out of them randomly select 2. If you have 100 gates, you randomly select 20 out of them. And those 20 gates you fold 3 times. So you fold like this, but you randomly choose 2 out of 10 gates and you just fold them 3 times. This is what it means. So what it does is that it restricts the increase in depth. Now all the gates are not folded. So it is not like if you take lambda equal to 0.2, it is not like this will be 3 times the entire depth. It will be much lower. The increase in depth is restricted. So now we can use this for ZNE for way deeper circuits. And that has been done in the literature already. One more good thing to know, where ZNE doesn't work. So ZNE works really well, I mean, but there is a particular regime where ZNE fails. Think of depolarizing noise. I never correct this. I'm so sorry. As P tends to 1, when my probability of error tends to 1, that means as I keep making my circuit bigger and bigger, what happens is, remember what is my depolarizing noise model? It is this, where Px, Py, Pz are the same. And when they are same, you can write it as identity by 2. Identity by 2, that is a completely mixed state. So it is as good as saying that you can just toss a coin and look into the outcome and say 0 or 1. You don't even need a quantum circuit. So in this scenario, if you take a Z-type observable, then if you go to identity by 2, the expectation value will be 0. Try this out. If that is not obvious to you, please try that out. That when you have identity by 2, and if you do an expectation value with Z, the expectation value will be 0. Now the point is that what it means when you have a depolarizing noise, and as you start folding your circuit, your signal is going towards 0. That's how you fit, that you had some non-zero value, and every time you are folding the circuit, it is taking your expectation value closer to 0. And then you fit and see what is the rate of that change, and you extrapolate to get the ideal or mitigated expectation value. Now, if your original circuit, the original ideal expectation value is already 0 or very close to 0, now your ZNE cannot work, because your original ideal outcome, say, is 0 or very close to 0. Now and then you are folding is taking your expectation value to 0. How do you really observe how the rate of changing going from 0 to 0, or something that is very close to 0 towards 0? So even if you do this kind of folding, then you don't have sufficient information to do the extrapolation. And therefore, if you go to circuits whose original value is 0, expectation value, then ZNE fails. There is no immediate way out of this. You have to look into circuits where you expect that your expectation value is not going to be 0. That's where ZNE will do very well. A second thing, there is one issue with ZNE and partial folding, as I said. So let's think. I am going to take 3 partial foldings. Say 1, lambda equal to 1, 1.2, 1.4. So what will this 0.2 mean? It will mean you take 10 gates and out of that randomly select 2 of them. Now let's say that I have a very big circuit. If it is a very small circuit, then if it is sufficiently small circuit, then this type of gate folding idea works very well, and you will immediately understand why. But let's say it's a pretty big circuit, which is like using almost the entire hardware. Now think, if I ask you that, oh no, you have 4 qubits. Would you use this, or say 5 qubits? Would you use this, or would you like to use this? I'm sure you will say I will use this because this one seems more noisy. For smaller circuits, you have the luxury of saying that I am going to avoid these bad qubits, bad edges, and I will transpile my circuit somewhere else. But for bigger circuits, when your circuit is almost extending to the entire hardware, you don't have this luxury. So now when you sometimes you use a very good edge, sometimes you use a bad edge. Now let's say that you run your circuit, and when you randomly select 2 out of 10 gates, you select this edge and this edge. Next time when you run, you select this edge and this edge. These two scenarios are very different. Even if you have this 1.2, 1.4, when you are going to do a fitting, so you need 3 noise factors in general. That is a practice. You go for 3 noise factors. Even during 3 noise factors, when you are doing 0.2, if you select these 2 out of 10, and in 0.4, if you end up selecting say 1, 2, 3, 4, the two outcomes will be very different, and then your fitting will be totally messed up, because the noise of the gates in these different experiments are very different. If that happens, your fitting gets messed up. What to do for that? We can do what is called as probabilistic error amplification. We'll very quickly go through this and we'll stop with this today. Let's say that this is my circuit. This is essentially a Hamiltonian simulation circuit. So this is my circuit. Instead of looking into individual gates, so if you look into individual gates, they will have their own different noise profile. What if I look into the entire layer and take an average of that? So someone has more noise, someone has less noise, but if I use the entire layer and average things out, then this more noise, less noise, sometimes I select good edges, sometimes I select bad edges, this kind of randomness will go away. So what is done is, again, we won't go into detail of this. This can get very complicated, this learning thing. So what is done is, we first identify the unique layers. See, this layer is repeated here also, here also. So when I say unique layer, I only need to know this layer and this layer. These two are the unique layers. The same layer is repeated again and again in the circuit, but the unique layers are only two. For these unique layers, I need to learn the noise in the system. So I learn what is the noise over the entire layer. And this is done something by sparse tomographic method. Let's not go into the detail of this. This is a bit complicated. The idea mainly is that you represent this as a Lindbladian, where only nearest neighbor interaction is allowed, and then you do a tomography with this relaxed Lindbladian. So let's not go into that. But I learned the noise in the layer. What it means, no more saying that this is maybe a good edge, this is a bad edge. I just take the entire layer as a whole. The moment I take an entire layer as a whole, instead of folding gates, now I will fold layers. So now the noise increases in an average fashion. So the same thing, see, this is the same thing. It is basically ZNE, but uh, instead of repeating gates, I repeat layers. So that way I avoid that sometimes good gates are repeated, sometimes bad gates are repeated. I avoid those kind of scenarios. I just repeat an average again and again. And then the same thing, this is noise factor 3. I can do noise factor 5 and I'll extrapolate. So this is probabilistic error amplification, and this method was first used in the utility paper in 2023. So if you are planning to do large circuits, I hope you are planning to do that. You should be doing that. But if you are going towards large circuit, it is always advisable to use probabilistic error amplification instead of the gate folding approach of ZNE that I showed before. But the idea is same, the principle is same. Instead of repeating gates, I repeat layers and then I extrapolate. That's all. So these two are kind of two of the main error mitigations which are used today. Two other error mitigations have been demonstrated in the Quantum Developer Conference like 1 week back, last week, I think, but we are not going into that. This is again a very, very powerful error mitigation technique. So maybe we can just stop here, and if there are questions, we can look into the questions, or else take up tomorrow. The way tomorrow we will take up is, I kind of said one thing, that an assumption is that when you increase the folding, be it PEA, be it ZNE with gate folding, the nature of the noise doesn't change. And I say that I am not going to answer anything related to that today. This assumption, how valid it is, if it is not a valid assumption, what do we do about it? This is what we will start with tomorrow. So, but if you have questions up to today, we can look into that.
Thank you so much, sir. I request participants on behalf of Ritajit sir. If you have any question for today's session, you may put it in the chat box. So I think there is no question on the go. You already have addressed all the questions.
I just
So-
remember like 2 or 3 weeks back, all these fall fests were ongoing, and I was in ISER Kolkata, and I was talking of this error mitigation only there. And when I asked, "Do you have any questions?" they didn't ask any questions. I said, "See, two things can happen. Either you have understood everything that I said, or you have understood nothing that I said." And then there was a professor. He said that, "No, why are you thinking so classically? It can be a superposition of both." So,
yes, yes, definitely. Uh, one question is there, sir.
yeah. Can you repeat why gatefolding is not used for large circuits? Yes. So main idea is that when you go for gatefolding for large circuits, you have to go for partial folding. Right? Let me just share once more. It will be easier. Yes, you have to go for partial folding. Otherwise, first and foremost, then the depth will just increase too much. So you have to go for partial folding. Now, when you go for partial folding, let's say that you are taking say 2 out of 10 gates randomly. Now the choice of gate and the noise profile of that gate, that can actually change between trials, first thing. And the second thing is, um, the second thing here, that is one thing. The second thing here is that even between say 1.2, 1.4, or even between when you are taking multiple shots, the choice of the gates, these things, if they differ, then what will happen is that the extrapolation will get completely messed up. So that's why it is better not to fold gates like that, but rather to look into the entire rather look into the entire channel together and learn the noise. I think there was a related question, why not take a weighted average? Yeah, that's a very good question. Thanks for this question. The reason of learning the noise here is something that we didn't discuss and we won't discuss. There is a error mitigation technique called PEC, probabilistic error cancellation. The idea of that is that if you learn the noise like this, and if you just invert the noise, see, doing the weighted average will not work. Why? Because when you do the gate thing here, if you take the weighted average of the gates, you are only accounting for gate noise. There are many other noise. And as I said, like there are many noise that I showed in the beginning, types of noise, and there are many other noise which I didn't even mention here. So when you learn the noise, it is not only learning the gate noise, it is learning the entire noise in the system without worrying about which noise is coming from where, what is it called. Let's not worry about anything. Let's have the entire thing as a single noise model. So when you do that, you get the entire information. Ideally speaking, you want to invert it, that is PEC, probabilistic error cancellation. If you can invert it, then what it shows is that you can actually do complete error mitigation. You can theoretically guarantee that you can do what error correction can do. It is that powerful, PEC. But it has a huge sampling overhead. So the number of times you need to run the circuit grows exponentially with the number of qubits and the number of gates. Since that becomes very difficult, so instead of saying that you want to invert the circuit, what it does is that let's increase the noise in the circuit and then extrapolate, because we already know it does great. So that's kind of the reason of learning the noise of the system and not taking a weighted average. And yeah, hope that answers.
Okay, so I think we are done for the day. So I would like to thank Ritajit sir on behalf of all the participants and as well as the coordinators that you have taken your time out of your busy schedule for this session. And definitely the session was also fruitful. tomorrow also the sir will be talking about the same thing, whatever is left. So with this, I thank Dr. Ritajit Majumdar as well as all the participants who are continuously being engaged in discussing all the doubts and all the concepts, making the session more engaging. So thank you all. Thank you, Ritajit sir.
Thank you.
So
Thank
we
you.
will be meeting tomorrow at the same time
Yeah.
from 3. Thank you, sir.
Thank you. Bye.
Bye.